Okay, more on waves. So this is the third video, and we're going to talk about wave types, different categories of waves. All right. We know about some of the terminology we need to use. We know about wave speed. We need to know about different types of waves. There are different categories. Okay, so for example, two main categories that you need to know. We've got transverse waves and longitudinal waves. Okay. Now we need to know how to define these things. We use the direction of a wave as a reference in both cases. Okay, we're going to compare the direction of the vibrations to define longitudinal and transverse waves. So if our arrow there is representing the direction of energy transfer, okay, if you want a fancy word for it, propagation, okay, but that's simply direction of a wave. And typically we might think about a water wave, which is a classic example of a transverse wave. They have a direction. We can watch a wave go by. They're quite large and slow, and we can actually see those. Okay, if you think about a pond, you might think about a football that you kicked into the pond. It's going to bob up and down. It's quite difficult to get a football out. Okay, you can chuck a stick at it and make waves, but it tends to bob up and down irritatingly. Likewise, you might want to think about a rubber duck in the bathtub. Okay, it bobs up and down. Okay, so the direction of wave in this drawing goes left to right. I'm thinking about the vibrations going up and down. The important thing to point out here is that the vibrations are at right angles to the direction. Okay, right angles, that's 90 degrees. Or we could use the word perpendicular. Okay, that's a classic word to describe the particles relative to the direction of the wave. Classic example of a transverse wave is water. You can also have electromagnetic waves. So electromagnetic, and they include visible light, radio waves, microwaves. There are 7 types of electromagnetic wave we're going to learn about in the next video. Electromagnetic waves are really important, and they are all transverse. Another example is an S wave. An S wave, the S stands for secondary, and it is a type of seismic wave or earthquake. All right. Now, longitudinal waves, okay, it's a slightly different type of wave, and instead of drawing them like a typical wave, you might see them drawn as a series of compressions. Instead of having peaks and troughs, we're going to have a succession of compressions and not compressions. And the easiest way I found to draw them is like that. So I've got a compression here. I've got another compression here. I've got another compression here. I can still have a wavelength, by the way, because I can measure maybe, let's say, from the middle of a compression to another like point. The next like point is to the middle of another compression, would be my wavelength from a longitudinal wave. I could, just as well as that, I could go from the beginning of a compression to the beginning of the next compression. Remember, wavelength was measured from similar point to similar point. But we need a name for this bit between the compressions. So instead of things being squashed together, we've got things stretched apart. Decompression would be a good word, but it's not the word you need to know. The word you need to know for this is rarefaction. Not a very commonly used word, so it's easy to forget. you need to know that word. Okay, we've got compressions for the squashed together bits. We've got rarefaction for the stretched apart bits. Okay, if we looked at a particle, let's think of a particle of air. The vibration is going to occur left to right on this drawing, which is parallel to the direction of the wave. Okay, the oscillations, the vibrations are actually in the same, they're kind of going long ways, aren't they? The direction is going long ways, the vibrations are long ways. That's a longitudinal wave. Another way of describing that relationship is the word parallel. Vibrations are parallel to the direction of the wave. Okay, you need to get those the right way around. They love testing you on this. It's quite a popular question. Okay, and you just need to learn it. Right, good example of a longitudinal wave is sound. So I mentioned that just now. An air particle might vibrate, okay, left to right on this diagram, which is parallel to how I've drawn the direction. Sound is your classic go-to example. If you want another example, another type of seismic wave is a P wave. The P stands for primary, because they're the first waves to arrive because they are faster than the secondary waves. Okay, there are two different types of seismic waves. So just saying seismic wave as an example of longitudinal is not good enough. It has to be a P wave. P waves are fast. They can travel through solids and liquids. Okay, unlike secondary waves, which can only travel through solids, and we use these as evidence, very strong evidence of the structure of the Earth. Okay, Earth's got a liquid outer core. Okay, and it tells us that about the structure of the Earth. We can go in that in a bit more detail, but basically it's good evidence for the structure of the Earth. Messy little sketch here, which doesn't really mean very much. Okay, but bear that in mind. There are two types of seismic waves. So if you're going to use seismic waves as an example for longitudinal waves, choose P waves. They're the primary waves, not S waves, because they are transverse. Quickly before I wrap this little bit up, we need to know that there are two other categories of waves based on what we are vibrating. Okay, if we are vibrating particles, we're talking about mechanical waves. So mechanical waves are any waves that are using a medium. Okay, they are using particles. A medium is required, i.e. particles, some kind of substance. Particles are required. So water requires water particles. Sound needs particles of air. Otherwise you won't hear sound. Sound does not work in a vacuum. No one can hear you scream in space. All right, sound is basically transferring energy from one air particle to another. It's a mechanical wave. It's using particles. Well, how can we have waves without particles? It doesn't make any sense. Well, actually, electromagnetic waves get their name from the fact that they are vibrations of electrical and magnetic fields. Okay, electromagnetic waves are vibrations of electrical and magnetic waves. They do not need particles. Okay, well that's handy, because otherwise how else would we get energy from the sun? Okay, we get heat from the sun, that's a type of electromagnetic radiation. We get light from the sun, electromagnetic radiation. That has to travel through millions of miles of space. Okay, without electromagnetic waves we would be sunk, we would not be able to survive. Okay, so we get our heat and light because we have vibrations of electromagnetic waves transferring the energy from the sun to Earth. Okay, So obviously, electromagnetic waves are incredibly important, and that needs to be discussed. So the next video will be on electromagnetic waves. You need to know about those. You need to know 7 types, etc. So look out for the next video. Be certain that's a very popular topic to be tested on in your GCSE. So there we go. Transverse waves, perpendicular, longitudinal waves, parallel. Know some examples. Okay, and then I'll see you in the next video.